Is the world geometrical? Apparently it is, since the notion of distance plays such an important role in our existence, and we are surrounded by all kinds of surfaces and volumes, all the way up to theoretical physics, with its geometrical definition of space and time. So one is tempted to conclude that our perception of a geometrical world might be nothing but a reflection of a true geometric nature of reality. However, this view is challenged by many physicists, not least due to serious mismatches between general relativity and quantum physics, and moreover, neuroscience suggests that rather than plainly seeing the world as it is, brains run simulations of the world fed with stimuli from the sensory organs, so one may wonder whether even the seemingly solid geometric nature of things might be nothing but a consequence of that mental simulation. For instance, let's look at a wall. The wall looks like a geometric surface, but we never see points of the wall. Each photon that hits our retinas carries information about a region of the wall, no matter how small. So the picture of the wall as a surface with points is a mental image. The aim of this talk is to describe a mathematical mechanism that may underlie such a mental creation of geometry in terms of a simple model of consciousness which is based on a mathematical definition of a space of qualia. Using such a model, hypotheses can be formulated, physical and information theoretical, concerning cognitive abilities of organisms that may explain the emergence of geometric mental pictures. As a baby step, let us address a relevant class of topological spaces, namely so-called second-countable locally compact Hausdorff spaces. It's a mouthful, but the details are not needed in this talk. Loosely speaking, qualia are the moments of subjective experience, or rather, following Lewis's definition, they are the ineffable qualities of those moments. Therefore, by definition, the same quale can be repeated over and over again. No reductionist hypotheses are needed regarding how qualia may or may not be reified in terms of known physical phenomena. Qualia are primitive notions in the theory described in this talk. In particular, they do not depend on any predefined notion of agent or observer. Qualia just occur. Another definition due to Lewis is that of a concept. Let us think of concepts as being the finite pieces of classical information which can be physically communicated and stored, for instance in brain synapses. Whereas qualia can be naively regarded as being the purely mental stuff, concepts are the physical stuff, and a natural hypothesis to adopt regarding the relation between these two types of stuff is that qualia leave imprints in the physical world in the form of concepts, for instance changes in synapses following a moment of subjective experience. So the mental can affect the physical. A mathematical approach to qualia is to describe the structure of the collection of all the qualia, the space of qualia. Begin with a set Q whose points are the qualia. The relation to concepts is an axiom of the theory, and it allows us to give a concrete definition of concepts as subsets of Q. Each concept is the set of qualia which can cause that concept to be a physical imprint. For instance, the concept Alice is red contains every experience of redness associated to Alice, such as seeing a glorious sunset or seeing Bob blush, etc. Note that referring to Alice does not mean that qualia must depend on a predefined agent, so there is no loophole regarding what I said before. The expression Alice's qualia is simply a way of referring to those qualia which are pragmatically linked to an entity called Alice, which in fact can emerge from the space of qualia. But I will not address that in this talk. There is also a concept, Bob's Red, containing Bob's Red experiences. If Alice and Bob communicate, they may agree that there is a more general concept, Red, which contains the union of their respective red experiences and does not belong to either Alice or Bob. Which subsets of Q can be concepts? The finiteness assumption in the above axiom says that the formation of concepts in response to qualia must use only finitely many physical resources. This creates constraints, namely, the collection of all the concepts must be what's known as a topology on Q. So Q, equipped with its set of concepts, is a topological space. This is an idea borrowed from the study of programming languages in computer science. What properties should this topology have? So far I have said that qualia leave imprints in the physical world, hence establishing a causal link from qualia to concepts. However, it can be argued that a link in the opposite direction should exist too. In order to see this, let us admit, for the sake of the argument, that a newborn is able to see light, but initially without being aware of different colors. Slowly, however, after repeated exposure to light of various wavelengths, the baby will begin to recognize different colors because his or her brain has been sufficiently modified. That is, some concepts have been stored. Hence, the changes in the physical realm, that is, the concepts, enable the color qualia to occur, which means there is also a causal link from concepts to qualia. This is the meaning of the axiom being displayed. Qualia and concepts are interdependent. This implies that any two qualia which trigger exactly the same concepts should be considered the same. But there is more. Any topology, and the concept topology in particular, is a model of a logic whose conjunctions are intersections of sets and whose disjunctions are unions. The models of such a logic are the truth valuations, which are maps from the topology of Q to the set of truth values, false and true, here represented by the empty set and the singleton set. This in such a way that the logical structure is respected. In particular, each quale Q defines a valuation V sub Q by assigning the truth value true to a concept if and only if Q can trigger that concept. This mapping is injective due to the previous axiom, but it might not be surjective. That is, there might be valuations which are not of the form V sub Q for any quale Q. This is undesirable because it shows that the logical structure of concepts allows one to infer that a quale should exist where in fact none can be found. So we add another axiom, and Q becomes a so-called sober space. The topological structure of Q models the interdependence of qualia and concepts. We have concluded that Q should be a sober space, but in order to describe rich conscious experiences, more mathematical structure is needed. Some cognitive capabilities, such as memory, may enable an organism to be aware of repetitions of qualia. For instance, there is a conscious experience associated to the aha moment that occurs when we realize that the quale Q was followed by the quale Q prime, hence giving rise to a primitive notion of time. I will ignore this type of repetition in this talk and consider only the type in which the same procedure is executed a few times in independent runs. For instance, if pressing the same button several times will on some occasions produce a flash of red light, and on other occasions a flash of blue light, we may have an aha moment in which we become aware of the existence of these two alternatives. I will call the quality of such an aha moment a disjunction of qualia, and will use the notation shown in the slide. Mathematically, if we follow the definition of disjunctions in a precise way, we are led to the conclusions in this theorem. Any two qualia have a disjunction, and the resulting binary operation is continuous for the concept topology. Moreover, the disjunction of two qualia is their supremum in the specialization order of the topology, which is that order in which a quale is said to be greater than another if it can trigger more concepts than the other. Sobriety and the existence of disjunctions implies that Q is in fact a complete lattice, that is, every subset of Q has both a supremum and an infimum. This is a very unusual kind of topological space from the point of view of a geometer. It is not even a Hausdorff space, which is the type of space where, such as on a sheet of paper, any pair of distinct points A and B can be separated by disjoint open sets, whereas in qualia space this is not possible because, for instance, any concepts that contain either the qualia blue or red must also contain their disjunction. So, where does the mental image of a geometric space come from? The answer is, at least for the baby step promised in the beginning, provided by three hypotheses. One is of physical nature and concerns our inability to perceive quantum interference directly. The second is entirely related to information processing capabilities, and the third is a bound on our ability to subjectively experience our own concepts, saying that being aware of a concept depends on our ability to discriminate that concept. For instance, if there were no non-red experiences, the concept red would be trivial, and there could be no subjective experience of it aside from the universal experience of just being. Let's go over these three principles one by one. For the first one, the fact that Q has infima means that there are conjunctions of qualia. For instance, red conjunction bright would be the joint realization that bright red light has been seen, whereas red conjunction blue might be impossible, so represented by the least element of Q, denoted 0. The hypothesis that no interference should be seen by macroscopic beings such as humans translates to distributivity in the subspace of Bob's qualia. The rationale behind this is not too different from that of classical logic versus quantum logic. Let us look at the second hypothesis. Due to distributivity, the sort of quantum-like and seemingly paradoxical behavior whereby measurements can contradict previous measurements does not occur. In the present context, this means that we can pretend that each quale adds new knowledge about an imaginary stable reality, hence making qualia look as if they were states of a computation whose observable properties are the concepts. So, acquiring more and more concepts becomes conceptually analogous to a classical computational process, and the mathematical ability to compute with infinite quantities such as real numbers by finite approximations has the mathematical consequence, well known in the study of the semantics of programming languages in computer science, that the complete lattice of qualia must be continuous and countably based, and thus, being distributive, it is isomorphic to the topology of a unique space S, which is both second countable and locally compact. So qualia are now mathematically represented as open sets of another space, but the points of that other space are not qualia themselves. This brings us back to the wall example. Each quale associated to looking at a wall is the subjective experience of seeing a region of the wall, because no photon can carry information about a single point. So no direct perception of the wall exists other than these qualia, which are mathematically represented as open sets of the wall. The points, however, are a mental construction. They are a figment of the imagination. So the question is, how does this mathematical representation of points arise in Bob's subjective experience? After all, Bob's feeling that the wall has points is itself subjective experience. How does it exist? Let's concoct a possible mechanism. Both the topology of B and B itself are topologies. So a sensible representation of concepts by qualia should be described by a map from concepts to qualia that respects the logical structures given by unions and intersections. Such a map is necessarily the inverse image mapping of a continuous map from points of S to qualia as required. For instance, consider this map phi. For each concept U, phi of U is the disjunction of all the qualia Q which are completely distinguishable from some qualia Q prime in U. Metaphorically, the qualia phi of U can be said to feel like the boundary of U. As I mentioned earlier, one can only have a feeling of the concept red because, by comparison, some experiences are definitely not red. The associated continuous map F assigns to each point X the open set of all the points which can be completely distinguished from X by means of disjoint open sets containing the points, in other words, by means of completely distinguishable qualia. Let's keep the map F at the top and compare it to another well-known map, P, which to each point X assigns the disjunction of all the qualia which do not contain X. This distinction between X and a qualia Q is much weaker than the one appearing in the definition of F, for it applies to any point X which is a boundary point of Q, which, despite not being in Q, is, let's say, as glued to Q as possible. But, since we are assuming that Bob's mind behaves like a computer whose states are the qualia, it is questionable that Bob's mind is able to make such a sharp distinction, as all he is able to do is tell apart qualia from other qualia. So, a sensible axiom is to assume that the maps F and P are the same, which is mathematically equivalent to S being a Hausdorff space, hence making the space S the second countable locally compact Hausdorff space as envisaged. The approach via qualia spaces is top-down in the sense that it tries to find abstract mathematical patterns underlying features of human conscious experience, in the case of this talk, that of perceiving a geometric reality without being involved in the nitty-gritty of neuroscience. A question is, which other animals have cognitive abilities that match the hypotheses of this talk? What about individual plants or forests? What experiments can be designed so as to test such conjectures? Last but certainly not least, this talk has been agnostic concerning the question of what qualia per se are. In qualia spaces, they are a primitive notion. Perhaps they are a fundamental element of reality, perhaps of the same nature as quantum measurements, but in essence, this is again the hard problem of consciousness. So this is a good place to stop the talk. Thank you very much for your attention.